So I'm going to talk about collider physics, but before I start, let me just say a few things. So first of all, this is a very very big subject, as many research have been done over the decades, and I suppose many of you have done a little bit of collider studies as well, and frequently you thinking about collider studies, you're thinking about complicated plots, kinematical distributions, and larger Monte Carlo simulations. A lot of time coding and writing, yeah. So I think that is true if you wanted to, actually do the real thing, and it's very good you do it. On the other hand, what I'm going to do it here now is basically I'm going to try to focus on basically intuitions and the qualitative features, and basically trying to focus on how to estimate things and the basic pictures, and trying to do, if you want, the collider physics on pencil paper and so on. So I mean, this is not going to be, this knowledge is very important, and before you embark on some large-scale simulation and studies, you probably wanted to get some basic feeling first. Your basic feeling may be wrong by order magnitude, but shouldn't be wrong by 3 or 4 order magnitude. Okay, if your basic feeling is, this is within the striking distance, you can go try. Okay, otherwise you're wasting your time. So that is basically what I'm going to try to do here. Also. Yeah, so also there have been lots of, so I'm going to mostly focus on new physics, but there have been lots of studies of new physics phenomenology at the colliders. A lot of them are over the years have many details, signals of various new physics scenarios. So I'm not going to do that, and I'm going to, again, trying to focus on just the broad brushed features and so on. And those details are very important, they're very interesting, but they are probably really relevant after we discover something. There are lots of things like that. Okay, so yeah, what else I wanted to say? Also, there's another aspect of collider physics, which is that the key to discover anything really is to really have very good models of standard model background. I'm sure most of you know that. And especially at LHC, it's very complicated, right? So you have to, really do a great job. And that's the part, unfortunately, I won't spend too much time on. And it will be a different lecture. I'm going to focus on basically the potentials of probing new physics at the various colliders. So I plan to spend probably most of my time on LHC. I'm going to start with basics and talking about the rates and the kinematical features, and do a little bit, and then talk about the new physics reaches at LHC. And after that, I'm going to talk a little bit about future colliders, like the reaches of Higgs factories and the 100 TeV or higher energy proton colliders. Yeah. So now, if you want me to actually talk about something else or something extra, maybe we can talk about it in the discussion session, or maybe you can ask me, or let me know. We can still adjust what I'm going to talk about later. Okay. Okay. So let's see. Let's start with LHC. How do I do this? So I suppose you all heard about the LHC, right? So it's a Large Hadron Collider. Is this size readable in the back? Okay. All right. So so currently it's running at central mass energy 13 TeV. Okay, previously it has a 7 TeV and 8 TeV runs. Okay, so it was the 8 TeV run finally discovered Higgs. Okay, so but currently it's running at this energy. You know, from my generation, Hadron Collider is a large Hadron Collider is known as a 14 TeV. So you're probably still seeing a lot of figures with 14 TeV and so on. So, but yeah, apparently it didn't quite get there, but maybe they will try to get to 14. But 14 and 13 are not too different. So, and it's a ring on the border of Switzerland and France, and yeah. So let's. So there are lots of things we can talk about the machines, and I'm not a machine physicist, so let me not. I'm not going to focus on too much. Let me focus on just a couple of things that will be useful for us, also useful for us to know. The first thing is luminosity. The first thing, well, in addition to the center of mass energy, the next thing you want to know about the collider is its luminosity. Okay. So luminosity, that is proportional to, let me just write equation and I will explain. Something like that, okay? And so this is, let me draw a picture. So the protons are circulating in a big ring, and they comes in bunches. And n is the number of proton in a bunch. Okay, so n is the number of proton in a bunch. Okay, and for LHC currently n is about 10 to the 11. Okay, and f is the revolution frequency, basically the inverse of the time take a bunch to go around. Okay. For LHC, this is about well, this is certainly just determined by the size of the ring, okay, because these all move at the speed of light. And this is about 11 kilohertz. Okay, and let me see. K is number of bunches. Okay, in the ring. And currently, K is well, this is not approximately, this is equal to this. Okay, and so you see that these three things all tell you, basically just tell you how many particles have a chance to pass each other per unit time. Okay, the product upstairs, and A is the area of the beam. Okay, it's basically this. So this is A. Okay. So this is the luminosity, and so normally we don't really, you know, as a particle physicist, we don't really care about these things. But you know, I think this at least there's some basic number, you know, you wanted to have in mind. It just help you to listen to, you know, talks from when people talk about machines. So these are the few key numbers for luminosity. And obviously the number of collision events is luminosity times cross section. Sorry? Oh, I should say. Currently, there's no typical size of A. Depends on how much you focus. But A currently is about 16 micron square. Okay, that's the size of the radius of the beam, if you want. Well, maybe you can time pi or something. So, okay, that's the area of the beam. Okay. And then also you can see that in order to jack up luminosity, what is the useful thing to do? Right? First of all, the most useful thing to do is put more protons in a bunch, but there's some limitations, right, to do that. And you can also try to squeeze the beam more, and so on. Okay. So you see that this is important because you wanted to you get more events that way if you have a higher luminosity. Okay. We'll talk about in more detail what luminosity, how does the reach of Hadron Collider depend on luminosity. Okay. So the LHC luminosity. So I'll put this online, at some point. So you have all the figures, but let's just LHC luminosity. And so they are usually quoted there are a few things. One is the instantaneous luminosity. Okay, and that's literally the luminosity per unit time. It's given in this annoying unit, centimeter square inverse per second. Okay, I think as a particle physicist you hate this kind of units because now you have to talk to your GeV unit, right? So. But anyway, that's what the number usually quoted, so it's useful to, well, I should say 33 to 34. Depends on the a slightly more useful way. Well, let's see. Now you can also talk about integrated. This is usually quoted in the, just this is how much luminosity total have been delivered, over a period of time. And that sometimes is quoted in a slightly, or in a more useful unit. So because the cross-section, the unit is usually quoted in some barns, okay? So I actually have no idea what barn means. So, but it's some unit of area. So cross section has the unit of area. This is some unit of area, and a millibarn is defined as 10 to the minus 27 centimeter square. Okay. Also very uncomfortable. And it's slightly more comfortable to think it about, this is about 2.56 GeV. This is more comfortable because that's the unit you do your calculation. Okay. Huh?
I don't think you want the brackets on your first definition.
Yeah, sorry.
No, on the top.
Oh. Right. So this is more comfortable because you're doing calculation with GeVs. Okay, and what's more relevant for new physics, the cross section is so as we'll talk about later. It's typically a femtobarn. Okay, it's much smaller, and so now since the cross section is femtobarn. And the product of these two is number of events. It's useful to define this as inverse femtobarns. Okay. So let's just say 10 to the minus, 10 to the 34 centimeters square second square. This is equal to 100 inverse femtobarn per year. Okay. So currently, it runs at about this, I think. In the future, LHC has a high luminosity. So I don't know. So LHC in the 2022 maybe is going to project it to accumulate 300 inverse femtobarn of data. Okay, from now to there's shutdowns and so on, but there are these. Okay, and then there is the second stage, which is called the high luminosity LHC. Okay, which will, runs more like a 5 times 10 to the 34 level, and by maybe 2035, you will have a 3 inverse attobarn of data. Okay. So this is a bigger number than this. I hope you realize. Okay. So this is okay. Any questions about these basics? Okay. All right. Now let's start talking about hadron collisions. Okay, so proton come in, right? So we have proton and the proton come in, okay, and they collide, okay, and but these are GeV size object, okay. So most of the time they're just going to make a bunch of GeV stuff, okay. So just but that's not what we are interested in, okay. Not normally. What's actually happening for the hard collision is actually one of the things in this proton collide in one of the partons in that proton. And okay. And suppose this proton has a P1, this has a P2, and this guy has momentum P1 as a fraction of this one, and this guy has a momentum P2 as a fraction of this guy. Okay. And yeah. So, and that give you the hard collision amid all the, then there are GeV crabs all over it, okay? So those things we don't care about. They are important backgrounds for certain things, but let's ignore them for now. And yeah, so let's just set up some notation. E1 is E1 0, 0, E1. The P2 is E2 negative. And so center of mass energy, this is the center of mass energy, is E1 plus E2. Okay, this is the center of mass energy of these two protons. But again, from this picture, you see that's not the useful energy. Okay, those energies are, it's only the energy carried by the partons are useful. And so there is sometimes called a S hat. So everything has a hat, is the parton center mass frame, okay, which is different from the lab frame. Okay, so parton center mass frame energy, which is basically 1 plus P2 square, and you can show that this is square root x1, x2. Okay, it's just a fraction of the total energy. Okay. I hope most of you have seen this before, and if you're not, you can ask me questions later. Okay. Okay, so this is the center of mass energy, and then the particle coming out, right? So we need some kinematical variables to describe them. Okay. The most naive one will be just using the angle. Okay, by using this this angle here. Okay, but that's not the most convenient one typically. Okay, because as I said, the center of mass frame of the proton is different from the center of mass frame of the partons. Okay, the center of mass frame of partons depends on these fractions. Okay, and therefore, it's not very useful because and each collision has a different parton center of mass frame. Okay, in the z direction, there's a boost either this way or the other way in the beam direction. So it's useful to define something that is invariant under the boost in the beam direction. Okay, so you wanted to make some distributions with respect to that variable. That sometimes is more useful. Okay. So that leads us to definition of rapidity. Okay. So rapidity is defined as okay. Just take any 4 vector, the rapidity is defined this way. Okay. Now you can show that under boost okay along z direction rapidity shift by a constant. Okay, this is just a simple exercise of Lorentz transformation that you can show what this constant is. Okay, it's not very difficult. The interesting thing here is that if you make if I make a distribution with a sorry, let me write it somewhere. Distribution with respect to y. Okay, but because each so of course each collision distribution contains many collision events. Each event has a different longitudinal boost, but this is invariant. Okay, this distribution is invariant. Okay, sometimes it's more useful not to think about in these terms, but to think in terms of something called the pseudo rapidity, and this is defined as follows. In the massless limit, okay, in the massless limit, if the particle has no mass, and which is usually a good approximation in Hadron Colliders because the energy are much bigger than the final state particles that you produce, and y goes to 1/2. You just use that formula, cosine theta and this is okay. So this then usually this is defined. This is called a pseudo rapidity. And that's the one that frequently quoted, because in order to use that, you need to measure the energy and the z momentum, which is many times impossible. Okay, but in order to do this, you just need to measure the angle. Okay, so and this is called eta, the pseudo rapidity. Okay, so again, it's in the mass limit. This is just rapidity. Okay. So a typical collider, therefore a detector. This is there's something around the collision point. There's a detector, and the coordinates. So each particle come out at some angle. So we need some coordinates. Okay. So one of them we already decided is the pseudo rapidity. Okay, which is and the other one is obviously the azimuthal angle. Okay, that is also a good. So we usually envision our detectors something like a cylinder. Okay, and this is the azimuthal angle. And this is the rapidity direction. Okay. Or sometimes, if you see event display, they will just unfold this cylinder and put it on a plane. Okay. Where, yeah, this can be eta and this can be phi. Okay. So. So this is from 0 to 2 pi, and this is from formally from negative infinity from negative infinity to positive infinity. But usually the detector don't really cover everything, cover all the angles, because the beam has to come through. Okay, and therefore there's some limit, also acceptance and so on. Okay, so typically it's something like a -5 plus 5. Or -6 plus 6, depends on. And this is already fairly very forward and backward. If you can check with that formula, the theta is already very close to 0. Okay. And if a particle hits somewhere, and you have a hit, let's say there's a hit some here, so you see event displays like this. Okay, that the height of this bar is the energy deposit, for example. Okay, so these are just basic kinematics. We'll talk some more about kinematics, but this is just setting up the coordinate system. Okay. Now let's talk about how was the cross section is determined. Okay, so as we know that the collisions only happen between those two partons. Okay, so the first important quantity, do it here. So the first important quantity is the probability I have, or the probability density I have, in finding one of the partons carry that much of momentum. Okay, so let's see. So let's say F1 x1. This is the probability of finding a parton carries x1 fraction of momentum from incoming proton 1. Okay. From finding the first parton, the parton 1 in the incoming proton carry fraction of it. Yeah. So this is called the parton distribution function. PDF. Okay? And the one thing is that the disk is, so the first thing is that of Hadron Collider physics, the first difficulty you might think is that these cannot be calculated. Okay, this, I cannot predict these things from first principles. Okay, so not from perturbative calculation. It turns out also lattice calculation has some difficulty actually calculating this, although people are trying to do this with lattice. So far without too much success. Okay. However, these things can be measured. Okay, can be measured using scattering experiments. Okay, so which, you know, again, something I won't go through in detail here, but these things can be measured by, for example, scattering electrons from nucleus, from nucleons. Okay, so okay, the non-trivial thing is that these things are universal. Okay, means that you only need to measure it once. It's some intrinsic property of the proton. You can measure it from one set of experiment, and then you can use it everywhere. Okay, so that's why this approach is useful. Okay, with that, with this definition, you can show that for a collision process, let's say, yeah, so the 1 and the 2 going through a bunch of things. This is not very good. A bunch of things. The cross section is let me just write the answer. Oh. Okay. And first, let's talk about this. This is the center of mass, parton center of mass cross section, and this is from basically x1 p1 plus x2 p2. The particle was these, and then going through a bunch of things. Okay, and this is the thing you draw Feynman diagram and calculate. The second one, and these are the parton. These are the probabilities of finding this initial state from the parton, from the proton, and then you integrate over all possible x's. Okay, x from 0 to 1, obviously. Okay, so well, with the, yeah, is this okay? So in general, this is a function of x1 and x2, but that's the one that you calculate. Okay, so this seems to be intuitively okay, but it's actually a highly non-trivial statement. Okay, that the fact that I can write it like this is a highly non-trivial statement. It means that I'm viewing this picture, I'm actually viewing this collision in the picture that I have a proton here, has nothing to do with this proton, right? So it just come along and with its constituents, and this one comes along with the constituents. Then they meet each other, and somehow one parton, and then the second process is that then this is the collision. All the proton does is supplying these probability functions. Okay. But if you really think about how a process will be, it's very complicated. You know, the gluon can go everywhere. right? This even when they have not met each other, I can already send a gluon to the other proton and so on. So why is this can be written as a product, and why is the whole thing can be written as this product? That is highly non-trivial. This is the statement called the factorization. Okay. Intuitively, this happens because this happens usually when we care about is the high energy collisions, and this happens at some high energy or short distance, this part, and these are the long distance part. The collision happens in so fast, so short time scale, the proton doesn't know, the rest of the proton doesn't know about it yet. Okay, that's basic, yes.
So when I look at MSTW, other PDF, what they enter when they tell me that they're having NLO? So you're saying that this is measured?
Sorry?
Seeing NLO, NNLO.
Yeah, NLO, NNO is a definition that how you, first of all, when you extract PDFs from your experiment, and this, depend, well, you have to, you also do a similar calculation like this, okay? From some collision result, you extract PDF. Then it depends on whether you do this into the next leading order or, right? So that's the NLO PDF.
So it's a matching between the PDFs and
Yeah, it's the matching between the, well, there's some matching scale here, and right. So it depends on you carry that. There's, yeah. There's a. We can, if you want, we can talk about it in more detail. But there's a scale dependence, and for example, that scale dependence needs to extract it. It depends on you are working on the NL order or NNL order and so on. That's different. Yeah. So. And in principle, that needs to be consistent with the calculation of whatever hard energy scale, hard energy collision that you're doing. Okay. But again, so these are the long distance, intuitively, these are the long distance physics, these are the short distance physics. Okay. And the way we, yeah, again, be able to write this is called the factorization. And the fact that this can be factorized in most of the hadron collisions are intuitively reasonable, but theoretically unproven. Okay, and yeah, but we are physicists, so if it's reasonable, we use it. Okay, no, that's not the real reason. The real reason is that, well, I don't know whether that's a better reason. That we can only do it. We can only do calculation if we assume that's true. Okay, and we can compare. Most importantly, we can compare the result by doing calculation like this with experiment. They seems to work. Okay, yeah.
To what degree you would say it's proven?
It's only proven for very special processes.
Yeah, but if you can actually prove it, like how would you say it's proven?
That you need to have a systematical way of not missing any. So basically, it's, you imagine that the correction to this formula is something that's the long distance scale over the short distance scale. Okay, so and this is basically a statement that this is a systematic expansion in that one, and you want to be careful that you capture all the possible singularities in a very complicated, the most general process with arbitrary number of gluon exchanges, that you're not screwing up that expansion. Okay, that is yeah. So if you wanted to do learn the state of art of this, there's a set of lectures given by George Sturman. That he's certainly the big expert on this.
Quick question.
Yeah.
So to what extent this factorization is like good? How much percentage?
Well, to the experimental accuracy we have achieved so far, and this seems to work.
Cool.
Okay. Percentage depends on the process. Okay. Okay. And And I think from time and time, people suspect certain things. There are certain for process. There are some non-factorizable contribution and so on. I don't think any of those things have been. There are some certain things that's known to be not factorizable. There are certain observables in QCD that's known to be non-factorizable because you can identify a particular process that's violating this thing, and then they all need to do is not talking about those things. Okay, it's because we cannot. If something is not factorizable, well, we cannot really calculate it. Okay.
Yeah, how much is just worth saying that,
yeah.
that there are corrections you'd expect in order power of the lambda QCD divided by.
Yeah. So I think I said that. Yeah, there is a power expansion of the lambda QCD over the shortest. Yeah, that.
I think that was the question, though, maybe. Right.
Yeah. Yes. So. Okay. So let's just recap what we have done. So basically, you can already see something. Okay. Let's see. Yeah. So in general, a cross-section, let me just repeat it here, okay? A cross-section here is some fx1, fx2 times some this, okay? Something like this. And so these two are some pattern distribution functions. And so that's a product. And then, and this one is basically some matrix element times phase space. Okay, so I suppose you have all done some kind of calculation like this. Okay, it's matrix element squared times phase space. Okay, so there are a few important things about the phase space. Okay, that we need to aware of. Okay. Well, first of all, there's a phase space we will talk about in more detail, but there's also so phase space, and what's important here. So this is yes, and but phase space here contains a phase space integral, but also has a threshold. So there are two things. One is the phase space integral. So we'll talk about more about it. Then the second thing, there is a threshold. Okay, especially if you're thinking about producing heavy particles, you have to have enough energy to produce them. Okay, so there is a mass threshold. Okay, basically, your cross section only opens up when you cross enough energy to produce those massive particles. So these are the pictures that. So this is saying that although formally I'm integrating this x from 0 to 1, but I'm not. Okay, I have to have this fraction large enough in order to produce this particle. Is this okay? Produce some massive particles. So I'm only sensitive to some part of the PDF, not all of them. Okay, the PDF that has enough energy to produce those particles. Okay. Okay. Now let's. What should I do? Let's look at what the PDF look like. Okay. Let's have some picture what the PDF look like. Okay. Let's do that. So PDF, again, just some this is X, okay? So PDF looks, roughly speaking, look like this. Okay. I'll draw two components. Okay. So this is gluon. Okay. So this is small x, big X, and these are the quarks. Okay. And there's also, so these are the quarks, and there's also, and these are the Q bars. Okay, so proton has antiquarks in it too. Okay, so and it has lots of gluons at the small x, and the reason that so there is a so here is what we call valence quark. Okay, valence quark is dominated. So if you talk about really, if you're probing proton, trying to find a quark that carries a very large fraction. So sorry, let me just write. This crossover place is about 0.1. Okay, if you're asking for a quark carries more than 10% of the proton momentum, likely you're going to find a U, U, and D. Okay, and these are the valence quarks. But if you only ask for a small fraction of it, most likely you're seeing a gluon. Okay? And at the very small end, these two become, Q and Q bar becomes almost the same. Because at this part, this thing is dominated by the fact that the gluon can generate QQ bars. Okay? Again, to go into this business better, we need to talk about Arteridi-Parisi equations and so on, but let's not do that. Okay, so but this is the picture. Here, it's basically a loop factor. Yeah, it's basically okay. So this is what the proton look like. Okay, depends on which momentum you use to probe it, you see different things. And because this process is generate equal amount of Q and Q bar, and then at the very small x, Q and Q bar looks basically the same. Okay. Yeah.
Can you explain why there's a loop factor between the gluon and the quark as well as a way to think about it?
Yeah.
Dominates, but why loop factor?
Because this is alpha s, so this is basically, if you calculate splitting functions, this is this basically. Yeah, this is the probability.
It's not a loop factor, it's just space-based.
It's it depends on how do you think. Yeah, it's a or if you wanted to, you can think about this as this, the imaginary part of this. Then it's a loop factor. Huh? That depends on the energy scale. Also, I haven't mentioned that the whole thing, this whole thing depends on this is the energy scale. This whole picture depends on the energy scale you use to probe the proton, logarithmically. Okay, so if you probe it at a higher energy scale, it will tilt it a little bit. Okay, you will even see even more gluons basically. It will tilt it a little bit. Yeah. But to think of, so sorry. Yeah, where's the formula that I wrote? It's there. So we can already doing this with that. We can already try to estimate the cross section. But think about this way. It's still not the most convenient one. Okay. So there's a slightly better way to parameterize this this dependence. Okay. Again, by using that formula up there. But now let me define two different variables, okay? One is tau, which is x1, x2, x1 times x2. And this is obviously, this is just the ratio between center of mass and the parton center of mass energy and the center of mass energy. So this tau basically parameterizes which energy I'm using. Okay, this is useful again because remember we are going to talking about some productions of massive particles. We need enough energy to produce them. Okay, so this variable is the manifestly just telling you how much energy in the parton center of mass frame you have. And then I have x equals x1. Okay, let's just make that. So let's do that change of variable with that formula. And there is a Jacobian. So there is a Jacobian, which is and this is 1 over x. The Jacobian is. Then you can plug in this new variable. The cross section is this. Okay. So, and this quantity as a function of tau, or as a function of parton center of mass energy, is called the parton luminosity. Luminosity, to be distinguished from the actual luminosity, okay? But it almost acts like luminosity. The parton luminosity times the parton center of mass energy times parton center of mass cross section give you the total cross section. Okay, so there is also an integration over tau, but as we say, we'll see in a moment that this is a we'll talk about it right now, but this is a very sharp falling function of tau. And so essentially you are very just sensitive to a very small region of tau that's useful. Okay, you have to cross the threshold, but then immediately the rate drops very fast. So why don't we'll talk about what's that pattern. Well, let's talk about it now. Okay, let me just draw how many do I need. Okay. For example, like this. Like this. Okay. There's no color chalks, right? So there's okay. And this one is glue. Okay, parton luminosity is a combination of two PDFs. So two partons. Okay, so this is glue. Suppose I start out with a glue initial state. It looks like this. And this is QQ bar. Okay. And again, they crossed at some point, and the QQ bar becomes bigger than glue. Of course, this makes sense with a larger x, because larger energy, because now you're mostly seeing some valence quarks. And this is a QQ. Okay. Just not QQ bar. Okay. This is for proton-proton collision. And yeah, so they cross at a little bit here. Okay, they only cross a little bit here. Okay, so it's a slightly Okay, you have to, it's a property of this function here. So, yeah. Again, I should probably put this this on the website so that you have these figures. And huh? This is a function of tau or s hat. Depends on how you normalize the axis. No, so let's say for LHC, and this point, I need to take a look. This point is about 1.5 TeV. Okay? Sorry. Or tau equals to 10 to the minus 2. Okay? So this is for 13 TeV LHC. Or for, yeah, so this is for the figure I'm drawing is 13 TeV LHC. Okay? Again, yeah, so this number is sensitive to the fact that I do a 13 TeV LHC, but this number is not too much. Okay, there is still a dependence if you do it with, but there is only logarithmic dependence on this tau. So if you think about it in terms of tau, it's more invariant between various colliders. Okay, so but just since we're talking about LHC, so let me quote the numbers for LHC. Yeah. Okay, so this is where the glue and the QQ bar cross over. And another important fact is that this distance here is about a factor of 10. Okay? Again, for details you need to, actually I have to show you the figure and so on. Okay. And this is on some super log, this is on some log scale, okay? One more thing is that if I think about this as A, okay? Obviously, these are all falling functions of tau. Okay, much harder to find the partons carries a significant amount of energy of the proton. This A actually depends on what the energy is. Okay, depends on what the energy is. If so, okay, so A. Let's see. What do I do? Yeah, A is about 2 for tau about 10 to the minus 4. Okay, 10 to the minus 4, if you want, it's the center of mass energy is 1/100th of the proton center of mass energy. This is about 100 GeV. Okay, and it's about 3 around 10 to the minus 2, and this is about TeV. And really, what?
Keep going. Just bring me the chalk.
Oh. Thank you.
Still need chalk, unfortunately.
Okay. Thank you. And then really falls off, drop dead after that, okay? So it becomes, for example, it becomes 6 around 10 to the minus 1. 10 to the minus 1 is 1/3, it's about 5 TeV. Okay? At Hadron Collider, at LHC for 13 TeV. Okay? So the bottom line is you know that even this 3 means that this drops at a rate of 1 over energy to the 6th power. Okay, already at this point it's dropped pretty fast. At the smaller energy, 100 GeV, this is mass to the 4th. Okay, still pretty fast, but slower than this. Okay, so this is probably the most important, very important lesson to learn about these PDFs. So again, as I have already said here, PDF is a very sharp dropping function. Okay. On the other hand, you have no choice but you must cross some threshold to produce the particle. Okay. This mass can be this m here can be the mass of a new particle you wanted to produce, or it can be the kinematical cuts you have to impose. Okay. Suppose I wanted to have a jet harder than 100 GeV or something, then you have to have enough energy to produce a 100 GeV jet. Okay, so this mass or energy threshold, for each thing, everything we care about, there is a mass or energy threshold you need to pass. But once you pass that, you don't want to pass it a lot, okay? Because the PDF drops like a rock, okay? Your rate basically decreases a lot. So to a very leading order approximation, everything is produced right on threshold. Okay, so that's basically what this is saying.
Sorry, those tau dependencies are for which luminosity? For which part of luminosity?
Huh?
I mean, the part
Yeah.
of luminosity.
Again, they don't depend too much on the parton. They are more or less the same. Yeah, they're
Same dependence for UU and for UR.
they are slightly different.
Okay.
They are slightly, but they are not that different.
Okay.
Okay.
Which one of those two numbers is approximate?
Hmm?
Which one of those two numbers is exact?
So all of these are approximate.
No, I mean the point that the two curves are approximate.
This one?
Because 10 to minus 2 is 1.3 TeV.
Yeah, it doesn't depend on that much. Okay, so please gloss over. I'm going to do this quite qualitatively. So gloss over my second significant digit. Okay. Okay. So from this, we can already do an estimate on what does the reach of Hadron Collider depend on. Okay. So let's do that. Okay. So reach of Hadron Colliders. So let's remind ourselves a few things. So the cross section is parton luminosity times this. Okay? About this. Okay. I'm doing this very qualitatively. Okay? This is about tau to the A's power times this. Okay? And again, let's suppose I need to make a particle. Make a particle of mass m. Okay? So therefore, my threshold is really just at mass m. Okay, I wanted to do that. So my s hat has to be greater than equal to m. But mostly I'm just making it on threshold. As I said, it's on m. And but from dimension analysis of this sigma hat is what? Dimension analysis. 1 over m squared. Okay, so that's my dimension analysis. And okay. Huh? That's right. Square. On the number of particle, number of these new particles produced is what? This is n is sigma times luminosity. This is the actual luminosity, okay? This is the luminosity. It's unfortunate use of names. Okay, this is called the parton luminosity, the other one is called luminosity. Luminosity is the one that we talked about earlier. Okay, so but this is the number of events new particle produced. Okay, now let's compare the reach. Now let's compare the reaches. Let's consider two colliders, just for the for the sake of our argument, let's consider all two possible collider energies. Okay? Two ECM energies, E1 and E2. And also two running at two luminosities. Yeah, just two luminosity, L1 and L2. Okay? So, and the reach, suppose this collider can find a particle of with mass of m1, and this collider can find a particle of mass m2. Okay. Now at this point, I have to make assumption on what do I mean by reach. Okay. Let's compare these two particles. But at least a reasonable assumption is that the reach is the reach is defined by some fixed number of signal events. Okay? And I don't know, it's n0. Okay, let's say every time at any collider I produce a particle, if I produce 10 of them, I discover them. Okay, maybe not, but 20. Okay, produce some amount of them, I discover them. Okay, so some fixed number. So in order to have the same to compare, so at the first collider at M1, I produce this number of event. Okay. At second collider at the proton center mass of M2, I produce this number of events. Okay, now let's just equate them together. This means that tau 1 A, this is the proton center of mass M1 square L1 equals to tau 2 A 1 over M2 square times luminosity M2. Okay? And of course, tau is related to the, yeah. Now remember that tau is related to the, it's just M squared over S. Okay, all these taus are just M squared over S. It's the proton center mass energy. And plug them in, you see that M2 over M1 is S2 over S1 1/2 S1 over S2 L2 over L1. Okay?
In general, there could be different A's depending on which regime you are in.
Huh?
In general, there could be colliders could have different A's.
It could have different A's. I'm ignoring that. Yes, the A can be also slightly different, as you said, although, yeah. Anyway, so I'm ignoring that. There is a small difference in A as well. Okay, now we can take a look at some of these, the limit of these, right? So first of all, super leading order comment, because A is large. The second factor is not very important. Okay, it's only the first factor. Okay, so therefore, M2 okay, super leading order. Okay, proton collider reach scale with energy. linearly. Okay, so that's not a big shock. Okay, and there is a correction to that. Okay, in order to fully deliver, this factor really needs to be 1. Okay, so you need some luminosity, but it's it's not an important correction. The second factor is not important correction. Second, if let's talk about if it's the same collider, okay? S1 is equal to S2. It's the same collider. Okay? But I just running different luminosities. Okay, let's see how the reach goes. Okay. Then M2 over M1. Now the second factor really needs to do something. Okay, otherwise we get nothing. L2 over L1. Okay. Means that yes, you do gain by have more statistics. Okay. You do gain reach by statistics, but you gain slowly. You gain like some big root of something. Okay, of the ratio of the luminosity. Okay. So, in terms of LHC, you can do this. You can plot this ratio as a function of luminosity. Okay, based on that one, you know it's going to look like this. Okay, so there is a slow period. There initially you are gaining pretty fast, but later on you are slowing down. And okay, and this turning point, I'll say is 10th of inverse Hamilton bar. Okay, depends on exactly where you put the turning point is. Okay, and right, and we are here. So the LHC reach will progress slowly from now on. Okay, so next year's Morion is not going to be as interesting as this year's Morion. Okay, well, I don't know. So you heard about Morion conference, right? This is an annual conference where LHC experiments announce their results and so on. And well, there may be some hidden discovery they are not letting us know yet. But other than that, if you're just talking about standard reach for SUSY particles and so on, it's not going to go very fast. Yes?
Where is the high luminosity LHC?
Yeah, it's here. I don't know. Well, if the luminosity goes up by a factor of 10, it does make a bit of a difference if you look at that formula. Right. So if we can also put some finer plot. So let's say this is some colored particle. There's some colored particle. We can talk about this. We will talk about this more. This is some colored particle, means that this really explores the large A area. Okay. So this is a large A. Larger A. This means this is a larger A part, and so it grows like this, right? It goes even slower because the 1 over this power is big, right? Now there's some uncolored particle, and this is let's say uncolored, okay? And this A is smaller, just because the reach is smaller. Okay, where is my? Maybe I have erased that. It's still here. Yeah, now, it all depends on what your reach is. Okay, suppose your reach is already TeV, the A is this. Okay, you're saturating faster, suppose your reach is only this, then you are saturating slower, okay? But it's saturating nevertheless. It's not saturating. Saturating is the wrong word. It grows slowly, okay? You're also going, there's still this turning behavior, but it just happens later.
Question?
Yeah.
Do you think the high luminosity LHC is a good investment?
Let's talk about that later. We'll talk about that later. Maybe also in the discussion session we can talk about that.
Cameras are off.
The camera is on. Oh. It's a great investment. Yeah. Yeah. Yeah.
So you are basically trying to see like how heavy state you can actually probe in this block.
Yeah.
If the case is when the masculine is fixed, but just that the cross-section was small enough,
Yeah. Let's.
much brighter than.
Right. So let's talk about that later. I do plan to talk about that scenario. Okay. It's more like it's a more systematic dominated scenario. So that's a different. Yeah. So remember, my assumption is only need certain number of events, right? So you can have different assumptions. Should I stop now, or should I? Is there? Yeah.
Keep going.
Huh? Sorry. What is my official time? What is it? 12:45. Oh, okay. Still have a lot of time.
Could you comment on turning point in the uncolored case? Do you know what the numbers are?
Let me look at the figure. It's not actually not that different, but of course depends on how do you define the term,
Sure.
right? So
But
it's
if you define it the same way, like
well, I don't know. It's a slightly, I think we are also getting closer to that turning point. It's not very different. Well, it's all this power. You can work it out from that formula. It's just some power, right? So. Okay. Okay, maybe I will start talking about phase space, then we can wrap up. So okay, so the next thing I wanted to also mention, it's important for us to understand the cross section is there is a phase space integral. You do want to do, okay? So let's just briefly talk about the phase space. Two-body phase space, okay? So it means that I have something that produce two particles, okay? And I don't necessarily mean X is a particle. It's just some incoming momentum, okay? So the momentum is that and I suppose you have all worked this out, okay? It's in Pascal. So, but let me just remind you, d pi 2, I will write it in a slightly more, d pi 2 is basically it's 4 pi p1 over square root x squared. Okay. All right. And well, if you want to write in the Monte Carlo community, it's frequently written in terms of this function. Where lambda 1/2 is just some function. This quantity basically just computes the the momentum of the particle. So the momentum is fixed. This momentum and that momentum, the magnitude are the same and they are opposite. So it's a two-body phase space. And yeah, so basically the thing important here is that there's a pi here. There's a pi for the two-body phase space. Okay, 8 may change, but pi won't. Okay, so and this is 1, roughly speaking. So this is all important for your estimate if you wanted to. And one thing we can ask, since we know that most of particles are produced on threshold, so what happened to two-body phase space near the threshold? Okay, near threshold. And let's just assume P1 square is equal to P2 square is equal to M square for simplicity. Okay, otherwise the equations are getting longer. And so in this case, near threshold means that the available energy is 2m plus some delta square. Okay, I just have enough energy, a little bit extra. And in this case, you can expand this function to a Taylor expansion, lambda 1/2. Well, let me see, this is just this. If I assume the particle mass are the same, lambda 1/2 is just this. Okay, and this, yeah, and this is basically delta 1/2 over m 1/2. Yeah. But anyway, it behaves like a delta 1/2. The threshold opens up pretty quickly, behaves like delta 1/2. Okay, this is basically saying that you don't really pay that much from the phase space point of view to produce on threshold. You only pay like this. Okay, you do have to be a little bit over the threshold. You cannot be literally on the threshold. But because on the threshold, literally this is 0. But you don't pay that much. It opens up pretty quickly. Okay, this is from phase space. In principle, there's also a bit of a threshold dependence from the matrix element. Okay, but usually that's mild. Yeah. Okay. Wouldn't be too much worse than this. Okay, so this is at least for two-body production. Our intuition about producing very close to the threshold are still correct, and the two-body cross sections carries these factors, okay, other than the ones that integrates to 1. Now, what about three-body? Once we do three-body, we understand n-body. Okay, three-body. So this is let me give it a different name. Y mu goes to P1, P2, P3. Okay, again, I don't necessarily mean this is a particle decay to 3 things, but it's just yeah, this is the incoming, Y mu is the incoming momentum. And okay, I'm sure you can write the general form of so d pi 3 is 2 pi to the 4th delta function times I equals 1 to 3 d pi cube 2 pi cube to pi 0. Okay, so that's the phase space basically. It's not very illuminating to look at it like that. Okay, so this is delta. This is energy momentum conservation delta function, and its use, you can show that phase space can be written in a different form. Okay, slightly different form. To that, it's useful to think about that. Let me artificially decompose this phase space into two processes. Okay, let me decompose y goes to x plus p3 as the first step. Okay, again, I don't mean these are particles. I'm just grouping momentums. Okay, and then x goes to p1 plus p2. Okay. Of course, in real decays, these can actually be particles, but they don't necessarily. Okay. If I'm grouping it this way, okay, it's a good exercise to show that this is 2 pi, two-body phase space. Y goes to x plus p3 times two-body phase space. X goes to p1 plus p2, okay, and the dx squared. The invariant mass, the momentum, full momentum square of this guy. Okay? With the constraint, so the constraint on x is m1 plus m2 is less than okay. So integral of this is taken in this integral, in this interval. Okay. I mean, there's nothing special about this. It's basically just carrying out this integral, but with this in mind, and remember, then you can write this in terms of product of two delta functions, basically. Yeah. Okay, but you should probably do it. Okay, why is this useful? This is useful because we can now compare this with okay, first of all, d pi 3, I can already conclude by just counting the number of pi's. Okay, let's first do a counting of number of pi's. Okay, well, we can already do the counting of number of pi's up there, but doing it here is slightly easier. But it's 1 over 16 pi square d pi 2. Okay, times something of dimension energy squared. Okay. Well, if imagining you write this out and you count the pi's. Okay, that's this. And this is just coming from that, and you write one of these out. And the rest of them, this is just dimension analysis. You have something with the dimension of energy squared. Okay. At least, yeah. When energy is, yeah, so all the mass of particle, okay, if you want. And so, and this is obviously will be cancelled properly by the same dimension for quantities from the cross section. Okay, in the end you get a number, okay, you get a cross section. But this is the comparison between the two-body phase space and the three-body phase space. So roughly speaking, adding one more thing, you get 16 pi square suppression. Adding one more thing to the final state. Okay? Okay. So finally, let's do. Sorry, I'm already a few minutes over. So let me first. Finally, I'm just. Let's look at the threshold, near threshold behavior. Okay. Again. Near threshold. Okay, suppose I'm producing 3 particles. With equal mass. So therefore, y is about 3m plus delta square. Y square is 3m. Okay, then you can look at this. You look at this formula. Right, so we already know, but basically everything is so y is more than basically x plus m3 plus delta, right? So and then x is basically m1 plus m2 plus delta. Okay, so yeah, so this is basically x. So I'm making this kind of assumptions. In everything this is a little bit more than it. Okay, so just I'm using the same. Parameter as parameterizing how much I'm over the threshold. And so d pi 2, we already worked out from the previous exercise, right? D pi 2 goes like delta 1/2. Okay? And then we have a dx integral here. Dx integral here. Okay, but it's integral within this interval. This interval is the size of delta. basically. Okay? So dx squared give you a factor of delta, basically. Okay, or m delta if you want. Okay. And therefore, d pi 3 is proportional to delta cube. So not cube. Square. Okay? So there are this is the second difference between this and the two-body threshold. Two-body threshold, we said, it opens up pretty quickly. Okay? But this one is slower. Okay? So for three-body process, you actually pay a little bit more. Okay? You do have to be away from the threshold a little bit more than you do have to be above the threshold a little bit more than a two-body process. Okay? And then you pay actually a little bit more on the PDF. Okay, so there's some additional suppression from a three-body final state, just from this threshold behavior. Okay, I think I should stop now and.